So shall we start?
यस मैम हम शुरू करते हैं.
Sorry.
Yes ma'am, I guess we can start.
ठीक है. Okay. So I'll share my screen. Let me know if it's visible. Okay. So
Yes ma'am, visible.
ठीक है. So what we are going to do today is we are going to know more about overfitting, underfitting, bias, and variance, and we would look at the regularization methods. Okay, these three topics we are going to cover today. So let us start with overfitting and underfitting. So what is overfitting? We have been using this term a lot. So just I'll draw an example, simple example, so that you get an idea of what is overfitting and what is underfitting. You already know this probably, but we are going to discuss this in detail. Okay, this is the same graph that I'm having, and I am drawing this. This is uh, assume this is the same graph. Okay. So now to explain the difference between underfitting, overfitting, and uh, simply good fit. So this is, suppose I draw a line like this, which does not represents my data. This is called underfitting. And suppose if I'm drawing a line like this, which is exactly representing my data, or it can be something like okay. So this is called overfitting. If my line is too much, if my model is fitting all the points exactly, this is called overfitting. And what a good fit for this model would be if I am fitting a line like this. So this is called a good fit. Now why this is called underfitting, why this is called overfitting? So the idea is, suppose you have values which is, so underfitting is your model is representing, is not at all representing your data which original data reflects, and it is somewhat suppose it is a linear model. So it is h theta x is equals to theta naught plus theta 1 x, and equation for a good fit should be h theta x is equals to theta naught plus theta 1 x plus, okay, I'll write this one with another pen so that there is, okay, so equation for this one is, let's say h theta x is equals to uh, theta plus theta 1 x plus theta 2 x2 x1 x2, and equation for the third overfitting part is, why a strength is so much low today. And so on. So this, what is this hypothesis representing? This hypothesis is showing only two parameters and only one features. This hypothesis is showing two features and three parameters. and this hypothesis over here is showing multiple number of parameters. So there's no requirement of fitting all the parameters for this data. Why it is not required? Suppose I have a new training example which is over here. So what would be my next uh, uh, suppose from this uh, my next training example is over here. Okay, and I want to predict it. So according to this overfitted hypothesis, this model is passing from above point, not it should pass through approximately all the classifying examples, right? So what it is doing over here is it's not representing the actual it's representing the actual points, but in a way that it is not properly generalizing for all the points. It is specific for each and every point. Model is specific for each and every point. It is not generalizing for all the points. While in this case, suppose I have a point over here or over here, so it will classify all such points correctly. While in this case, if I have a point over here, over here, over here, so it is not classifying correctly. It should be something like model should be something like because my drawing is it should be something like this. Correct model should be something like this, right? So it is not generalizing for points which are not yet in the data. So this is called overfitting. When we are fitting a model and this model is only representing the current data and it is not fit for the data which we have not seen yet. That is, we call it as test data or unseen data. So this is not general. Or I can also write this over here. Not generalizing generalizing well, or we can say that not a good fit for uh, test data, for test data or unseen data that we have not seen yet. So this is called overfitting. Okay, simply this is called overfitting. Now when does overfitting occurs in our model? So whenever we have multiple number of parameters, if number of features, sorry, parameters, a number of features are extremely larger than number of samples that I have, number of training examples. This case happens in that this means I'm adding so many parameters like theta 3, theta 2, theta 1. So many features are there: x1, x2, x3, xn, and they are having a specific polynomial terms and so many other terms are there. In that case, we can say that it is overfitting. So if number of features are much more than the training examples, so what we can do to avoid this overfitting situation? So to avoid overfitting situation, we have several options. Now, first of all, after overfitting, let me explain the bias and variance. So this situation is also called as variance, high variance situation. High variance means too much varying with respect to mean. Variance is what? Variance is the distance with respect to mean. If I'm talking about variance, so this is how much it is different, how much is it uh, away from the mean, right? So this is called variance. So this overfitting is over here is basically high variance. We can also call this as high variance, and underfitting is called bias. This is underfitting was called high bias. So my model should neither be having high bias nor should be having high variance. It should be having a good mixture of bias and a variance. It should not pass through all the examples. It should generalize well for the present examples as well as the unseen examples. Okay, so it should be the balance of both high bias and variance. ठीक है. So now we are going to have a look at the overfitting, how to avoid this overfitting situation. Overfitting, how to do that, how to avoid it. So we have seen that first thing that we have seen was that if my features are extremely larger than the number of training examples, so first thing that I can do to avoid that is reduce the number of features. reduce the number of features. Now these features can be redundant features, or redundant features means, suppose I have date of birth and I have age, so both of these almost represent the same thing. So from my date I can calculate age, from my age I can calculate my date, so date of birth. So such features are redundant features, so there's no use of keeping all the features. Similarly, there can be some correlated features, okay, which are also not required. Okay, so what we can do is we can reduce all these features, remove these features, and reduce my x input vector. And if I'm reducing the number of features, in that case, it is possible to avoid overfitting. Okay. Second thing that we can do is regularization. So we are going to study regularization today. This is extremely good method to improve the to avoid the overfitting situation. And third we have is dropout, that you might have already heard. And fourth that we have is early stopping. So we are going to have a look at all of these today in this lecture. Okay, so let's start with regularization first. So in regularization we have regularization. So what was the problem in overfitting that I was facing? I was facing the problem that I have some hypothesis and it is representing theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and up to theta n xn. So the problem was, exact problem that I was facing was that high number of features. So what if I reduce these features? So reducing these features, so to reduce these features, one method we have seen that we can directly remove them, or we can apply some dimensionality reduction methods to remove these features. Okay. Second thing that what we can do is, what if I give these thetas extremely small value? If I am giving these thetas extremely small values, if theta is approximately equal to 0, this means if theta 5 is, let's say, approximately equal to 0, so this means the effect of x5 effect would be negligible. Effect of this feature would be negligible, right? So what is the idea behind regularization? Idea is that, suppose I have a set of features, I have multiple number of features, and I want to regularize the parameters. That is, I want to regularize the thetas such that I want to reduce the weights for reduce the those thetas where I don't want to keep those features. So those features which are not important, for that I can reduce the overall weights or overall parameter values. Okay, so this is what a regularization is. Now there are two types of regularization that we follow in this. Whether it is a this regularization is a general term, we can apply this to all the logistic regression, we can apply this to ANNs, we can apply this to any other model that we are fitting, any other deep learning model. Okay. So regularization we can apply whenever we see the overfitting. Whenever I'm seeing my model overfitting, I can apply the regularization. Okay. Now there are two types of regularization. So first one is uh, L1 regularization, and second one is L2 normalization, L2 regularization, sorry. This is L2 is also called as, I think, ridge or lasso. One of them is ridge and we'll see which one is ridge and which one is lasso. I think L2 is called as ridge. I'm confused in this, and this is called as lasso. Lasso regularization. Okay. This is just another name for this. Now let us have a look at L2 regularization. So in L2 regularization uh, For suppose I'm studying for logistic regression. So we have already seen that what is the cost function? What is the cost function for logistic regression? We have something like j theta is equals to what? Some j theta is equals to 1 upon 2m sigma I is equals to 1 to m for m training examples. Then I have h theta xi minus yi and plus, so this is regularization term. I is equals to 1 to n for all the parameters. I want to regularize this. Okay, so this is the regularization term. Now, what is happening over here is why this is called L2. We have already seen that L2 norm is x minus y square. So whenever I'm talking about something like if I want to calculate the distance from point 0, 0, it is something x square. This is L2 norm. We have already studied, and we have studied that L1 is sum of x, so this is L1 norm. Okay, so this is calculated as x1 minus 0 plus x2 minus 0 if the point is 0, 0 plus xn minus 0, and this is calculated as uh, x1 minus 0 square plus x2 minus 0 square plus up to xn minus 0 square. If my point is not 0, 0, 0, point is y1, so this would be replaced by y1, x1 minus y1, x2 minus y2, xn minus ym. So this is my L2 norm, general Euclidean distance, L1 and L2 norms. ठीक है, so this is general idea that we already know. Now this is why this term is, you can see over here, this term resembles to theta j square resembles to this L2 norm, right? So that is why this is called L2 regularization, and simply in L1 regularization we have only theta j square instead of squaring the term, we have only 1 to the power 1. So L1, in L1 you can see that there is only exponential is 1. So that is why in L1 norm, that is the only difference in L1 and L2. And in real life, we generally use L2 norm because we'll see why and why it is more important than L1 norm. So L2 is generally used. Now let us have a look at the overall gradient descent term that is calculated after applying this regularization. So what is the effect on the gradient descent algorithm? So my gradient descent says that uh, theta is updated for minus 1 by m sigma I is equals to 1 to m h theta xi minus yi. This is the simple term that we already do, and then we have x naught I. So this is, we have already studied that this is j theta. This is how we update weights in my logistic regression. And for theta naught we do this part, and for theta j we do, for rest of all the parameters we do again same sigma I is equals to 1 to m uh, h x theta xi minus yi whole square, then xj I for ith training example plus lambda by m theta j. Now where is this lambda by m theta j coming from? Over here for the 0th parameter I have not written this term because theta naught is we have hypothesis which is in the form of uh, h theta x is equals to theta h theta x is equals to theta naught plus theta 1 x1. So this is free from the feature term, so there is no feature over here. So for theta naught we don't need a regularization term, right? We only need regularization term for, so we don't need this part. We only need regularization for rest of the thetas, which is theta 1 to theta n. So for theta naught we don't need a regularization, right? So over here where this lambda by m theta j is coming from, so recall that what do we do while calculating this uh, uh, thetas. What is the actual thing that we do? So this theta, this weight update parameter is updated, this weights are updated by theta minus alpha d by d of some theta. ठीक है, and that theta is with respect to cos function that we have, right? Theta naught, theta 1 up to theta n. So this is what we do. So this is a gradient, this is the actual, so this formula is coming from this equation, right? These two formulas. So this is gradient. So up till here, up till this point we already know the gradient. This is for my logistic regression. So if I'm calculating the gradient for the remaining term, that is this part, lambda I is equals to 1 to n theta j square. If I calculate the gradient of uh, d by d of uh, sigma I is equals to 1 to uh, sigma j is equals to 1 to n theta j square. So this is my that term if I am calculating theta. So what will I get? So I'll get something like 2 2 theta j, and I'm also having this parameter over here. You can see lambda outside. I have this lambda outside, right? So this lambda over here I already have. So this lambda is over here. So this would be lambda 2 2 lambda theta j, right? Now where is this 2 uh, why we have removed this 2? Because we have been dividing it by 1 by 2m, so outside. So this whole, so my whole term is converted, this my whole term is basically converted to, if I multiply this with 1 by 2m, so this whole term would be converted to theta by m theta j, sorry, lambda by m theta j. This lambda is over here is called regularization. uh, Lambda is called the regularization parameter. Regularization parameter. ठीक है? So I hope you are not getting confused with this part. Uh, So over here we have, what we were doing was we are basically multiplying 1 by 2m, and it would become lambda by 2m sigma of theta j square, and if I take the gradient of theta j square I would get 2 theta j, and that 2 would be cancelled by this 2. I would get lambda theta by m. So that is what I'm getting over here. Okay. So this is how my weights get updated during the gradient descent function, gradient descent cycle. The process remains same for the neural network as well. So same thing you are doing for the neural network. You are just adding this term, which is n I is equals to 1 to n theta j square, and you are just updating the weights by lambda by m theta j. That is the only difference that you are going to do in the neural network. Now let's have a look at the again. So we have done with the L2 regularization. Now let's look at the L1 regularization. So L1 regularization is exactly the same. The only difference is that in place of 2 here you would get 1. In place of 2 you have 1 as exponential. Okay. And similarly over here you would not get this theta j, because you have if you take the gradient descent, okay, I will write that down. So this would become so I hope this regularization thing is clear to you. If so, this L1 regularization. So my equation becomes 3 theta is equals to minus 1 by m uh, sigma I is equals to 1 to m yi log, okay, I will write h theta, chalo ठीक है, h theta x I plus 1 minus yi. This is for logistic regression, log 1 minus h theta xi. ठीक है, we already have this equation for logistic regression. uh, so what is the addition over here is you will just be adding plus lambda by 2m sigma I is equals to I is equals to 1 to n theta j instead of theta j square. ठीक है, and in place of this this cos function lambda by mj you will get, because if you do gradient descent or if you do apply d by d theta for this whole part, this part which is regularization, L1 regularization part. So if you do lambda by 2m sigma is equals to 1 to, no, it is outside, by 2m sigma I is equals to 1 to n theta j. So this would be lambda by 2m only. ठीक है, so in that theta is removed from that whole equation. So what we can see is while updating the weights, my weight updation is dependent on lambda in regularized L2 regularization, while in L1 regularization my weight updation is not dependent on previous previous theta, right? So in L2 regularization my weight, this lambda updation in this lambda or what you call as updation in the regularization is dependent upon the previous values of thetas, while in L1 regularization this is not dependent upon previous value of theta. So that is why in this L2 regularization this is also called as weight decay. Weight decay because at every cycle of gradient descent these weights are getting decayed. Weight is basically thetas, so these thetas are reduced at every cycle, because at next cycle theta is a multiplication of previous theta as well as previous lambda, right? So at every cycle multiplication, if you multiply 0.1 0.1 0.1 it would become 0.001. So that is why these parameters are getting reduced in the L2 norm. That is why this regularization, L2 regularization is more popular than L1 regularization. Now how to set this value of lambda? So if you are setting this value of lambda is equals to let's have a drawing that is pen of another color. Okay, so suppose I am having how to choose this lambda. If uh, suppose if lambda is extremely large, in that case what will happen, and if lambda is very small, like approximately 0. So if lambda is 0, that means no regularization, that you are not doing regularization at all. And if lambda is extremely large, it makes all the parameters, all the features reduced to zero, this would make model under fit. So lambda should not be extremely large and it should not be zero. Zero means you are doing no regularization at all. Okay. So it should be somewhere in between. Now this was the regularization part. Another thing is a dropout. That is also very important. You might have heard this term, drop out. So we do drop out again to avoids overfitting. How? So dropout, as the name suggests, suppose you have a neural network which is having this kind of structure. Uh, so what does dropout uh, basically gives? It removes some nodes from the whole. Instead of learning the whole network, what it does is it basically removes some nodes. Suppose this has removed this node, and this node. Sorry, not output node, because there would be no output then. So this node, so randomly it has removed, suppose, these four nodes. Now this your neural network has become a simply linear function of this node, this node, this node, and this node. So now it has become a simple linear function. So that is why this dropout, because instead of doing so many multiplications of all these features, what it is doing is it is simplifying your complex function. So simplifying the complex function, that is what we wanted to do. Complex function. So what we wanted to do was we wanted theta 1 plus theta 1 x1 plus theta 2 x2 up to theta n xn and somewhere square or cube or something like that. We want to reduce this complex function to some simple function, uh, reduced to some simple function, theta 1 x1 plus theta 2 x2, simply. So this function is reduced. So that is why this situation avoids overfitting. This whole uh, uh, dropout avoids overfitting. So we use dropout whenever we feel like my model is overfitting. So in that case we use dropout. Now how do we select the value of which nodes to delete? Which nodes to delete? This is selected randomly. So randomly some nodes are deleted. Okay. And what is the value of how to set the key probability? Key probability is suppose 1. So this means let me have a look at uh, so key probability basically decides the what are the chances. Key probability decides the chances of keeping a node or a neuron. Okay. So if key probability is 1, that means all the nodes in the network are kept in the whole network. So none of these nodes are deleted. Okay. And key probability is equals to 0.5, let's say 0.2. So this means that there is a 20% chance that a particular node is deleted or a kept. Suppose okay, we'll discuss this first. Let's see if key probe is 0. So if key probe is 0, this means that we are not using any neuron, and my input is directly my output. So none of the nodes are kept. Nodes are kept. Now let us look okay, now let us have a look at, suppose my key probe is 0.2 or 0.3, something like that. Suppose my I'm setting uh, suppose I'm setting key probe is equals to 0.3, suppose. Okay. So what does this means? So this means that first of all, we calculate for each and every neuron, we calculate some activation value for this one, for this one, for this one, and then for final load, we calculate for this. So for if for this node, if I want to uh, I have a set of activation. Uh, I have total, let's say, 5 nodes, or let's say 2 cross 3 nodes. I have. Okay. So there is a so if I my probability is uh, uh, suppose this is 2 cross 5. Okay. So I have 10 values over here. 10 values over 10 values of activations over here. In my total number of activations for the neuron are 10. Okay. So if keep probe is zero point 0.3, this means that there is a 0.3% chance that I will keep a node. So out of 10, only 3 nodes I will keep and 7 I will not keep. So I will drop out 7 nodes. So 1, 2, 2 cross 5 is there. 1, 2, uh, 3, 4, 5. 1, 2, 3, 4, 5. So I am deleting 1, 2, 3, 4, and 5, and 6 and 7. So only these 3 nodes are kept. So this is how I decide. So some randomly I have deleted 7 nodes and I have only kept 3 nodes. So this is how I decide the dropout. So dropout should not be very high and it should not be very low, because in this case it is zero point 0.3. So it is only keeping 30% of the nodes. All the 70% are going to, not used. Okay. So that is okay, but depends on the model that you want to build. Okay, so this is another method to reduce the overfitting. So we have seen 3 methods. First method was to delete number of features which may be redundant, which may be correlated, which maybe you can use dimensionality reduction and other methods to remove the features. So feature set should be reduced. First thing. Second method was regularization, out of which L2 regularization is extremely popular, and it is used to give to reduce, basically penalize. We also call that penalizing the parameters. Basically penalizing means reducing the values of the parameters, making them to value to making that those values to zero, approximately zero, so that their weights are not counted, not effective in the model building. Okay. Third overfitting method that we have is dropout. So in dropout, we randomly delete some node to simplify the function, to simplify the overall hypothesis, so that my network final output function is not overfitted for the whole data set. Okay. So this is what, so in dropout, whenever we are learning model again and again, some new random nodes are deleted. So if first time this node is deleted, in second time this may be the case that this first node is deleted. Okay. Or second node is deleted. So some randomly at every iteration we are selecting a random deletion of the nodes. So so this is another method. Now there is one more method which is also which can also be used for overfitting, which is early stopping. So it is nothing else, we
I have a
just
doubt.
yes, pucho.
I mean, isn't dropout like upload to every layer, applied to every layer?
Isn't dropout applied to every lab coding?
I'm every layer. I'm like it's applied layer wise, right?
uh, it's layer by layer. Yes, right, it's layer by layer. It's not I have just given this example, this weight matrix. It is for each and every layer, because it is for every yes.
And ma'am, what does deleting a node mean? Like, do you set the probability, like the probability of it to 1 or 0? Like, do you drop like that? Like, you initialize like a random sort of array of zeros and ones, and then some of them are zeros and some of them are ones.
हाँ, actually what happens is देखो, जब suppose I have a layer ऐसे, I have some value. This is my matrix for activations for 3 nodes, suppose. ठीक है. 3 nodes are there, and I have set the keep probe to 33% or maybe 0.33. ठीक है, so 33% nodes I will keep, and keep I will 0.33 and discard, that is 0.77, right? So this is my node, and activation value was, let's say, 0.3, 0.9, 0.5 for these three neurons that was I was having. So first thing that I would do is I create a random array of zeros and ones, and in those zeros and ones I will keep 33% ones and 77% zeros randomly. So I will set 0 1 0. ठीक है, so 33% is done. Now I will multiply these and I will get some value which is 0, 0.9 and zero point 0.5. So this 0. So I will get this value. This means this node neuron number 1 and neuron number 3 is deleted. This means actually it is not deleted, only the values are removed, only values are converted to 0.
Yes, ma'am, got it.
हाँ, ओके, ठीक है, एंड सो लेट्स
ये
कम।
की प्रोबेबिलिटी कैसे डिसाइड की, रैंडम है या फिर ये खुद से कैसे डिसाइड?
यस, हाँ, आप खुद से यू कैन डिसाइड ये सारे पैरामीटर्स वाइल लर्निंग द मॉडल। जैसे आप लर्निंग रेट डिसाइड करते हो, जैसे कि यू डिसाइड द लैम्डा रेगुलराइजेशन वैल्यू, यू डिसाइड द मोमेंटम, you decide the number of layers, you decide so many things are there na. So similarly
ओके,
there is keep, so you have to learn the model and you have to check. ठीक है, okay, so let's come to early stopping. So we have seen that my model is working fine if my value is reducing at every iteration. If my loss or error or cost, whatever, if it is reducing at every iteration, my model is working fine. This is for training data, right? And for testing data it should also perform similarly. Test data. Now what happens in some case, after a particular iteration, instead of going to this way, my model starts moving this way. Okay, so for test data this may happen. So we say we try to retrain it for training, and then we try to retrain it for testing, we try to do so many things. But if you feel that number of iterations over here were sufficient, let's say 50, or some iteration number of iterations were sufficient, so you can stop your model and you can say, okay, at this point my model is, because at this point, at this iteration, your testing and training errors were approximately similar. So when you get the training and test train error is approximately equal to test error, this means sometimes it's okay that, okay, and you have a definite number of iterations. It should not be that you have only run your model for only one iteration. So you have run your model for sufficient iteration, and you have training and test error which is approximately same. So what we do is, we early stop our model, and we don't train it for more number of iterations. We don't move forward and we say, okay, this is my optimum point, and at this point I can say model is performing fine. So this is also another example to avoid overfitting, because after this point my model is overfitting, because test error is extremely high and training error is low. This means that my model is not generalizing for test data. Okay, so this is also called early stopping. So here this can also be used for avoiding overfitting. Okay, so this was it for today's lecture. And while you have any questions, you can for sure ask me. Okay, morning class. That is why students have not joined, huh? And there is also no quiz today. This is also the reason, right? ठीक है, okay. So any questions? Everything is clear, I hope. Fine, let me download the attendance and you all can leave. Okay, so let's dismiss this meeting.
Thank you, ma'am.
Okay, welcome.
Madam, you can end the recording.